गुड आफ्टरनून बच्चों। आज हम कोलिगेटिव प्रॉपर्टीज का लेक्चर नंबर 2 लेंगे। लास्ट टाइम हमने डिस्कस किया था कि व्हाट आर द वेरियस कोलिगेटिव प्रॉपर्टीज, और उसमें से हमने डिस्कस किया था रिलेटिव लॉवरिंग ऑफ वेपर प्रेशर एंड एलिवेशन इन बॉइलिंग पॉइंट इन सम डिटेल्स। सो जैसा कि आपको मालूम है, कोलिगेटिव प्रॉपर्टीज दे आर नथिंग बट दोज प्रॉपर्टीज ऑफ द सॉल्यूशन, दोज प्रॉपर्टीज of a solution that is having some non-volatile solute plus a volatile solvent that is in liquid state, which depend on number of solute particles only, which depends on number of solute particles only and not on their nature, not on their nature। इसका क्या मतलब है कि सपोज मैं आपको 1 kg वाटर दूं और 1 kg वाटर में मैंने डिजोल्व किया से 10 ग्राम ऑफ glucose, then 10 gram of sucrose and 10 gram of say urea. Okay, now what will happen to the colligative properties, that is the say elevation in boiling point. As we know that the glucose molar mass is 180, sucrose it is 342, that you can find out. Sucrose is nothing but C12H22O11, glucose is C6H12O6, and urea it is 60, and urea is NH2CONH2. So delta TB, if we calculate, that will be molality into Kb, that is the molar elevation constant for water, which is constant, that is 0.52 Kelvin kg per mole. So this elevation in boiling point is directly proportional to molality, and what is molality is number of moles per kg of solvent. So we see that the number of moles of sucrose will be least and the number of moles of urea will be maximum, because this molar mass is minimum among the three. So what we can say is that this delta TB for sucrose will be less than that for glucose, and that will be less than that for urea. Okay, because number of moles will be maximum in urea and minimum in sucrose. So this trend of delta TB will be there, and that will be the same trend for elevation in this depression in freezing point, as well as the relative lowering of vapor pressure and the osmotic pressure. Same trend will be followed, because all are the colligative properties. So we can say that the colligative properties depend only on the number of molecules. So number of molecules of a substance is directly proportional to number of moles of that substance, because 1 mole of any substance contains Avogadro's number of molecules, that is 6.022 into 10 to the power 23 molecules. So higher the number of moles, higher will be the number of molecules, and higher will be the value of colligative property, whether it is your elevation in boiling point or depression in freezing point, or it may be your depression in freezing point, or it may be the osmotic pressure, or it may be the relative lowering of vapor pressure, that is P1 naught minus P solution upon P1 naught. Okay, these are the four colligative properties, that is your elevation in boiling point, depression in freezing point, osmotic pressure, and the relative lowering of vapor pressure. So all these four properties, they will depend on the number of molecules of the solute particles, or we can say they will depend on the number of moles. Okay, because this delta TB is nothing but molality multiplied by Kb, that is the molar elevation constant. Delta TF is equal to molality multiplied by Kf, that is the molar depression constant, and that this Kb and Kf, they are the properties of the solvent, so they depend on the solvent. Like for water, this Kb is your 0.52 Kelvin kg per mole, and your Kf is 1.86 Kelvin kg per mole. This for water. So similarly for other solvents, these Kb and Kf values will be different. Okay, so and this relative lowering of vapor pressure is equal to x2, where x2 is the mole fraction of non-volatile solute present in the solution, and osmotic pressure is given by pi, which is equal to mRT, where m is the molarity of the solution, r is the ideal gas constant, that is universal gas constant, and T is the absolute temperature in Kelvin. So this will give the value of pi, that is the osmotic pressure, which we will discuss later on. So now it is clear that whatever be the colligative property, whether it is the elevation in boiling point, or it is the depression in freezing point, or it is osmotic pressure, or it is the relative lowering of vapor pressure, all of them are somehow related to the number of moles, whether we say molality, or we say mole fraction, or we say molarity. Okay, so they depend on the basically the number of moles, because number of moles will determine the number of molecules of the solute present in the solution. Now let us understand this graphically. Okay, suppose I plot this vapor pressure versus temperature. Say this is the curve for pure solvent, and this is the curve for solution. So this is your solution, and this is the pure solvent. Now you see this at a given temperature, if you see at this temperature, what is the vapor pressure of the solution is this one, and what is the vapor pressure of the solute, that is solvent, that is this one. So we can see that the solution vapor pressure is less as compared to that of pure solvent. Okay, now if we see the boiling point, then I draw a line horizontally. So suppose this is the 760 torr in case of water. Suppose this is the curve for water, then water has a vapor, this at 1 atmosphere it is 760 torr, and we know that the boiling point of water is 100 degrees Celsius at 1 atmosphere, that is at 760 torr. So if this is the water and this is the pure solvent, then this temperature will be 100 degrees Celsius. And what about this? This is the boiling point of the solution at the same pressure, and we see that this is higher than 100 degrees Celsius by this amount by this much. Okay, so 100 degrees Celsius is the the boiling point of the pure water at atmospheric pressure, and for the solution it is higher than 100 degrees Celsius, because as the vapor pressure of the solution is less than that of the pure solvent, so its boiling point will be higher than that of the pure solvent, because this solution, to make the vapors from the solution to get 1 atmosphere pressure, we have to heat it more, so its boiling point will be higher than that of the pure solvent. So with this, suppose I want to show the freezing point. Okay, I want to show the freezing point, that is depression in freezing point delta Tf, which is small m into Kf. Suppose I want to show this graphically. Again I will draw vapor pressure versus temperature. So this is the curve for the, say, pure solvent, and this is the curve for the, say, solution having some non-volatile solute. Now what we will see, suppose I am cooling this solvent. Okay, so when I am cooling this solvent, its temperature is getting reduced. Okay, so this was the, say, 100 degrees Celsius here. Say, let us take the case of water, which is, say, 100 degrees Celsius at 760 torr pressure. Suppose I am cooling this solvent, that is cooling the water, so its vapor pressure is getting reduced. As the temperature reduces, the vapor pressure is getting reduced. Suppose here I get the pure ice. Okay, here it gets frozen, say 0 degrees Celsius. Okay, so the temperature here is, say, 0 degree Celsius, so it has frozen. Now it will not follow this same curve that was for the liquid. Now the curve will be different, that will be for the solid, and for the solid this curve is somewhat steeper, so it will be like this. It is steeper than that for the liquid. Okay, so we see where this is the vapor pressure of solid, how it is varying with temperature. Now you see, if we extend this curve, then this is the freezing point for pure solvent. Okay, and this is the freezing point for solution. So we can say that the freezing point of solution is less than that of solvent by this amount. Okay, this is called the depression in freezing point. So it will be less than 0 degrees Celsius if I dissolve some non-volatile solute into the solvent, any solvent. It may be water, it may be benzene, it may be any other solvent. Now we will take few examples, numerical problems based on this elevation in boiling point, depression in freezing point, and the, say, relative lowering of vapor pressure, that is nothing but P1 naught minus P solution divided by P1 naught. Okay, so based on this we will take few examples. The first example is, it is required to calculate the mass of a non-volatile solute, the mass of a non-volatile solute of molar mass. That molar mass of the solute is given as 40 gram per mole. Okay, and that is dissolved, this non-volatile, this is dissolved in 114 gram of octane. Okay, what is octane? Octane is nothing but C8H18. Okay, so it is dissolved in 114 gram of octane, such that it lowers the it lowers the vapor pressure of octane by 20%. It is given that this lowers the vapor pressure of octane by 20%, and what we have to calculate is the mass of the non-volatile solute. So how we will do? This formula will be same, that is the relative lowering of vapor pressure. So what is the formula? P1 naught minus P of solution upon P1 naught is equal to X2, that is nothing but the mole fraction of the solute. Okay, now this is given to us as 20%, that means this value is 0.2 is equal to X2. What is X2? Mass of the non-volatile solute is not given, so let us assume that the mass of this is W2 divided by molar mass. Molar mass is given as 40. Okay, molar mass of the non-volatile solute is given as 40 divided by this number of moles of solute plus number of moles of solvent. What is number of moles of solvent? That is 114 divided by the molar mass of octane. What is that? 12 into 8 plus 18, that is 96, plus 18, that is 114. So this is 114. Now by this you can calculate the value of W2, and that will come to around 4. So it will be 4 gram. So that you can calculate and verify. Okay, so this is one example. Now let us take, this will come as 10 gram. So answer will be 10 gram. So that you can calculate. Now let us take one more example. So to make the concept clear, let us have 2 or 3 more examples. Now it is given that for an aqueous solution, these all questions have been asked previously in some IIT JEE exam. So it is given that for an aqueous solution means it is a solution in water. The freezing point is given as minus 0.186 degree Celsius, and what is required is elevation in boiling point of this solution will be, okay, option is 0.186 degree Celsius, then it is 0.052 degree Celsius, then is 1.86, and next option is 5.12 degree Celsius. Now how we will do? They have also given the values of Kf, that is the molar depression constant, and the Kb, that is the molar elevation constant. They have given, this is given at 0.52 and this is given as 1.86 Kelvin kg per mole. Unit will be same. Now how we will do? We will apply the formula delta Tb equal to molality into Kb, and delta Tf is molality into Kf. Okay, now because the molality has not been given, so we can eliminate the molality by these two equations. If we divide them, we will get delta Tb upon delta Tf, that will be Kb upon Kf. Okay, now delta Tf is already given to us. What is delta Tf? That is 0 degree minus 0.186, that is nothing but 0.186 degree Celsius. So what will be delta Tb that is required? That will be delta Tf multiplied by delta TF multiplied by KB KB upon KF. What is KB? 0.52 divided by KF, that is 1.86. So you can see easily that this is coming at 0.052 degree Celsius. So which option? Option B is correct. So with this we conclude our session. I hope this concept of colligative properties like elevation in boiling point, depression in freezing point, and relative lowering of vapor pressure is clear to you. In the next section we will take osmosis and the osmotic pressure, that is the fourth colligative property, that we will discuss in the next section. Okay, thank you.